So, good morning students. So, ಇವತ್ತು ನಾವು haloalkanes ಮತ್ತೆ haloarenes ಬಗ್ಗೆ ಮಾತಾಡೋಣ. Haloalkanes, haloarenes second PUC chapters ಇದು first organic chemistry chapter second PUC ನಲ್ಲಿ. So, haloalkanes is also known as alkyl halides. Haloarenes are also known as aryl halides. So, in haloalkanes, the hybridization in which halogen is directly bonded to the carbon atom, in which the hybridization of carbon is sp3. Whereas in case of haloarenes, halogen is directly attached to a benzene ring in which the hybridization of a carbon is sp2. So here in this chapter, if you go through with the points, we have plenty of points here. So the upcoming named reactions in this chapter is Finkelstein reaction, Schwarz reaction, dehydrohalogenation, Williamson synthesis of ether, and Gattermann reaction, and Sandmeyer's reaction. And apart from that, we have a very important point in this chapter called nucleophilic substitution reactions. And these nucleophilic substitution reactions can be explained by using two mechanisms. One is Sn1 and another one is Sn2. In case of Sn1 mechanism, the order of reactivity of alkyl halides is tertiary is greater than secondary, secondary is greater than primary. We know that Sn1 mechanism consists of two-step mechanism. So the first step is formation of carbocation, and the second step is attack of electrophile. So due to the formation of a more stable tertiary carbocation, so tertiary alkyl halide is more reactive towards Sn1, so rather than secondary and primary. So apart from these tertiary, secondary and primary, so the more reactive alkyl halides towards aryl halide towards Sn1 mechanism is so benzyl halide. So benzyl halide also more reactive towards Sn1 mechanism, because so during the formation of a carbocation, it loses X minus, forming C plus. So this is what benzyl cation. Benzyl cation. Remember, among all carbocations, that is tertiary, secondary, primary, simple, and benzyl. Benzyl carbocation is more stable. Due to the formation of more stable benzyl carbocation, benzyl halide is more reactive towards Sn1 mechanism. Why it is more stable? Because of involvement of resonating structures. In benzene we have alternative double and single bonds, and those pi bonds present in the benzene involved in the resonating structures. Hence this benzyl cation is more stable than tertiary, then secondary, then primary. Hence the order of Sn1 mechanism will be like this: first benzyl halide, followed by tertiary, then secondary, then primary. In case of Sn2 mechanism, it will be reversed because it's a single step mechanism. So where attack of nucleophile and leaving group both can be takes place simultaneously. So that's why here the order will be primary, then secondary, then tertiary. So in case of Sn1 mechanism, we know that rate of reaction is directly proportional to alkyl halide only, not for nucleophile, because it is independent of nucleophile, where if in presence of strong nucleophile or weak nucleophile, so any type of nucleophile so can undergo Sn1 mechanism very easily. In case of Sn2 mechanism, so the rate of a reaction, that is slow step, so rate of a reaction is directly proportional to the concentration of alkyl halide as well as nucleophile, because here first nucleophile will attach to the carbon on the opposite direction. After that, the existing group will be going away. So that's why, so here we need a strong nucleophile. So in case of Sn2 mechanism, a strong nucleophile is required. That's why Sn2 mechanism is nothing but so nucleophile dependent on nucleophile. In case of Sn1, we can say that independent of so nucleophile. So in case of Sn1, so in the intermediate carbocation, so there will be attack of nucleophile in both the direction. So either in right side or in the opposite side or left side. So that's why we can form it can form a racemic mixture. So and it can form enantiomers also. So what are enantiomers? So these are non-superimposable mirror images of optically active isomers. So what are racemic mixtures? So equimolar mixture of both dextro and levoisomers are called racemic mixtures, and these racemic mixtures are optically inactive because in case of racemic mixture we have both dextro and levoisomers, and that too equimolar. So the angle of rotation created by dextroisomer will be compensated or cancelled by the angle of rotation created by levoisomer. So that's in case of Sn1, enantiomers are produced, racemic mixtures are formed, and it is independent of nucleophile, independent of the solvent. That means you can take either polar or non-polar, any one of the solvent in case of Sn1. So because already the CX bond is more polar in case of Sn1 mechanism. Why? Because of taking tertiary tertiary alkyl halide or benzyl alkyl halide. In case of Sn2 mechanism, the order will be primary, secondary, tertiary, and rate is directly proportional to the alkyl halide and nucleophile. We need a strong nucleophile in case of Sn2 mechanism, and it cannot form enantiomer. Why? Because only the nucleophile will attacks the carbon on the opposite direction, only in the opposite direction. So because of that, it can form only one type of isomer. So because either dextro or levo. So because of that, it cannot form enantiomer, it cannot form racemic mixture, and it is optically active. It require a polar solvent. Why here Sn2 mechanism require a polar solvent? Because here we preferably choose the primary alkyl halide in which CX bond polarity is less here. Because of less polar CX bond, we need a polar solvent. So if we make use of a polar solvent, the polarity of the CX bond increases. As a result, X minus will be going out very easily. OH minus will be getting inside very easily. So to create a polarity in case of Sn2 mechanism, we need a polar solvent, and strong nucleophile is required in the Sn2 mechanism. So whatever the points we discussed till now, that is Sn1 and Sn2 mechanisms, these are only for alkyl halides. If you take haloarenes or aryl halides, so the nucleophilic substitution reactions are very less. So generally we can say that haloarenes are less reactive towards nucleophilic substitution reaction. So why they can show less reactivity towards nucleophilic substitution reaction means we have so many reasons. Because of resonating involved in the resonating structure, and this halogen is electron donating group in case of benzene when it is attached to benzene ring. So that's why it can form a double bond because of double bond character, and because of formation of highly unstable phenyl cation. So all these reasons will be there. Less polar CX bond. So because of these reasons, haloarenes are less reactive towards nucleophilic substitution reaction. So however, we can say like this, with increase in the electron withdrawing group, reactivity towards nucleophilic substitution reaction increases. So again, an example for electron withdrawing group is NO2 group. If we go on increasing the NO2 group on the haloarenes, so generally the reactivity towards nucleophilic substitution reaction increases. So because of the presence of withdrawing groups, so the reactivity towards nucleophilic substitution reaction increases in case of haloarenes. So this is about nucleophilic substitution reactions in case of alkyl halides. So apart from that, we have so many chemical properties regarding alkyl halides. When they reacts with aqueous KOH, they form alcohol. When they reacts with alcoholic KOH, it can form alkene. And this reaction is nothing but elimination, dehydrohalogenation, also nothing but beta elimination. So in case of secondary alkyl halide, so if two beta carbons are present in a alkyl halide, so then we have to follow this important rule called ZF rule. According to this rule, during the elimination of alkyl halide, so during the elimination of HX from the alkyl halide using alcoholic KOH, an alkene with highly substituted product is the major product. If you take if you take 2-bromobutane reacts with alcoholic KOH, it gives two alkenes. One is but-1-ene, another one is but-2-ene. Between but-1-ene and but-2-ene, which one is more major product here? But-2-ene is the major product, because in but-2-ene we have highly substituted alkene. So that's why according to ZF rule, during the elimination of HX from alkyl halide using alcoholic KOH, an alkene with highly substituted product is the major. So similarly, if it reacts with silver cyanide, so KCN, it gives cyanides. AgCN, it gives isocyanide. So in case of KCN, it gives cyanide because of ionic nature. In case of AgCN, it gives isocyanide because of covalent nature. In case of KNO2, it gives alkyl nitride because of ionic nature of KNO2. In case of AgNO2, it gives nitroalkane because of covalent nature of AgNO2. In case of moist silver oxide, the formula of silver oxide is Ag2O. Moist means water. When any metal oxide mixed with water, it forms respective hydroxide. So hence moist silver oxide means AgOH. When this moist silver oxide reacts with alkyl halide, it forms alcohol. In case of dry silver oxide, it forms ether. In case of, if you react this alkyl halide with a magnesium metal, it forms a very important compound called organometallic compound. Example is Grignard reagent. The formula of Grignard reagent is RMgX, where R in the Grignard reagent can act as nucleophile. So apart from these alkyl halides, so we have still some more derivatives of alkyl, that is polyhalogen derivatives, where more number of halogens are present in our in the compounds, that is chloroform, carbon tetrachloride. Using this chloroform, we can prepare DDT, dichloro diphenyl trichloro ethane. So phosgene, carbonyl chloride, COCl2 is called phosgene gas. Chloropicrin, chlorine, nitration of chloroform gives chloropicrin. We discussed so many times in our PU classes itself. There is a preparation and properties of chloroform. Apart from that, so one of the very important compound of this alkyl halide is that is hydroxychloroquine, one of the chemical substance which we are using today to cure the coronavirus. So that is hydroxychloroquine. It is also one of the organic compound which containing halogen in the compound. So alkyl halides or haloarenes has a very wide range of application to prepare so many compounds. So the first question, we will see that an organic compound A forms B with sodium metal, and again A forms C with the PCl5. That means an organic compound A is taken, it forms B with the sodium metal, and again that A reacts with PCl5 giving forms C with PCl5. But B and C reacts together giving diethyl ether. So therefore A, B, C, R. So here let me plot the graph of this question. So here first initially taken A. So A can form B with sodium metal. If you react A with metal sodium, it gives B. So again A forms C with PCl5. So but B and C reacts together, B plus C reacts together giving diethyl ether. Formula is C2H5O, C2H5. So then what are A, B and C? So here the A will be a alcohol, because alcohol reacts with sodium metal, it gives sodium alkoxide, and this alcohol containing OH group reacts with PCl5, it gives alkyl chloride. So this sodium alkoxide and alkyl halide reacts together giving ether, that is Williamson synthesis of ether, we know that. So that's why A should be a alcohol. To prepare diethyl ether, we need ethyl alcohol. That means A should be a ethyl alcohol. When ethyl alcohol reacts with sodium metal, it gives a C2H5ONa, sodium alkoxide. Similarly, this ethyl alcohol again reacts with PCl5, it gives ethyl chloride. So when this ethyl chloride, so this is C and this is B and this is A. So when this ethyl chloride reacts with this sodium ethoxide, so it gives respective ether. This reaction is nothing but Williamson synthesis of ether, very important named reaction. When alkyl halide reacts with sodium alkoxide, it gives respective ether. Using this Williamson synthesis of ether, we can prepare simple ether as well as mixed ether. So actually this Williamson synthesis of ether follows Sn2 mechanism. So here it can form a nucleophile C2H5O-. That C2H5O- replaces the Cl- by attacking on the opposite direction. Hence it is a Sn2 mechanism forming diethyl ether. So option, so A is C2H5OH, B is C2H5Cl, and sorry, this is B and this is C. So B is C2H5ONA and C is C2H5Cl. So the right option here is option A. The next question is, chlorobenzene can be prepared by reacting aniline with. So that means we are going to prepare chlorobenzene using aniline. So using which reactants you can prepare chlorobenzene from aniline? So take aniline. So formula of aniline here is, I will write here. So take aniline. Formula of aniline is benzene with NH2 group. First it reacts, to convert this NH2 group into Cl, first we have to convert this into a diazonium chloride. So after that we can convert that into a Cl group. So how to convert this into diazonium chloride? So it reacts with nitrous acid, that is HNO2 at 0 to 5 degrees centigrade, or else you can take sodium nitrite and HCl also. So instead of taking HNO2 directly, you can take NaNO2 in HCl. So these two reacts together giving nitrous acid. First it forms a benzene diazonium chloride. So this benzene diazonium chloride reacts with cuprous chloride, that is Sn1 reaction. So that is Cu2 Cl2. So or you can take Cu2 Cl2 in HCl. So this also can be taken. So it forms a chlorobenzene. So aniline can be converted into a chlorobenzene. So by converting aniline into benzene diazonium chloride followed by the reaction of cuprous chloride, so it gives a chlorobenzene. So the right answer here is, so nitrous acid HNO2 followed by heating with cuprous chloride. So our next question is, for the reaction C2H5OH HX in presence of zinc halide, it gives C2H5X plus water. So just see here, OH of the alcohol is replaced by halogen. So it's a nucleophilic substitution reaction. So generally it is called Lucas reagent. So Lucas reagent. Lucas reagent is a mixture of, anhydrous zinc chloride and concentrated HCl. So here he is asking the reactivity of the HX. We know that reactivity of HX depends upon the bond length. So more the bond length, more will be the reactivity, because its bond energy is less. So if X is I, having more length with more reactivity, so that's why order of reactivity HX will be. So HI is more reactive than HBr, HBr is more reactive than HCl, HCl is more reactive than HF. So this is the order of reactivity of HX towards this nucleophilic substitution reaction. Hence in the given options, the correct order is there here: HI, HBr, HCl. So option B is the right answer. So next question is, alkyl halide cannot be obtained from alkane or alkene by reacting with. That means where you cannot prepare an alkyl halide using alkane and alkene by reacting with these. So here they given four options here. So both HCl and HBr can be used to prepare alkyl halides using alkene. So and this chlorine Cl2 can be used to prepare alkyl halide using alkane as well as alkene. But this PCl5 cannot be used to prepare alkyl halide using alkane or alkene, because so PCl5 is one of the chlorinating agent. So used to prepare alkyl halide only by taking alcohols, where the organic compound containing OH group will be replaced by Cl. So but here in case of alkane and alkene, we don't have any OH groups in the organic compound. That's why using PCl5 we cannot prepare alkyl halide using alkane or alkene. So that's why option is C, PCl5. So in the next question, in the following sequence of reaction, here they given a sequence of reaction: CH3 CH2 CH2Br. First it reacts with alcoholic KOH, it gives A. Next it reacts with HBr, gives B. B reacts with aqueous KOH, it gives C. So the product C will be. So let me see that. First we take on CH3 CH2 CH2Br, propyl chloride. First it reacts with alcoholic KOH. So alcoholic KOH acts as a dehydrohalogenating agent. It helps to remove the Br. So here Br will be there. So in the beta carbon I take an H here. So this is alpha, this is beta. So Br minus from here, H from here, HBr will be eliminated. So this bond shifts to here, forming a double bond. So it becomes CH3, CH double bond, CH2, followed by reacting with HBr. So it is Markovnikov rule. So during the addition of HX to the unsymmetrical alkene, negative part of the reagent is added to the carbon containing less number of hydrogen. It becomes CH3CH. Negative group will be added to the here. So it becomes single bond CH3, followed by reacting with aqueous KOH. So aqueous KOH used to substitute Cl by OH group. So this Br will be replaced by OH to give CH3, CH, OH, CH3. So hence the obtained compound is propane 2-ol. Hence the correct option in the given here is option D, that is propane 2-ol is the right answer. So next question is, a mixture of two organic compounds which is treated with sodium metal in presence of dry ether, it gives isobutane. Isobutane. So was obtained by as a product. The two chlorine compounds are, we know that three important named reactions, that is Woods reaction, Fittig reaction and Woods Fittig reaction. If you take two alkyl halides reacts with sodium metal, it gives a higher member alkane, this is Woods reaction. If you take one alkyl halide, one aryl halide, it gives Woods Fittig reaction. So in case of Fittig reaction, two aryl halides are condensed together. So here he taken two organic compounds which is treated with sodium metal in presence of ether, it gives isobutane. The formula of isobutane here is CH3, C, CH3, CH, CH3. So this is isobutane. So it is obtained by treating two organic compounds with sodium in presence of ether. So why we taken ether here? It's a non-polar solvent. So if you take polar water as a solvent, sodium immediately catches fire with the water. To avoid that, we taken so non-polar ether here. So which organic compounds we have to take here to get this isobutane? So this is one and this is one. So it gives CH3 Cl plus CH3 CH Cl CH3. So this is methyl chloride, this is isopropyl chloride. Both reacts together in presence of sodium and triether. It gives isobutane. Hence the right option, correct answer in this for this question is CH3Cl and isopropyl chloride and methyl chloride. Option C is the right answer. So in the next question, the order of reactivity of alkyl halides towards dehydrohalogenation. So I told you very clearly, dehydrohalogenation is the elimination, beta elimination reaction where HX is removed from the alkyl halide. So during this elimination, Br is removed from the Br minus is removed from the alpha carbon, H plus is removed from the beta carbon. So here halogen has to go as X minus. So if you remove X minus here, you will be getting a carbocation. So among all the carbocations, which carbocation is more stable? Benzyl carbocation, but it is not there here. So that's why tertiary carbocation is more stable than secondary. Secondary is more stable than primary. So then the order of reactivity of alkyl halides towards dehydrohalogenation reaction is tertiary is more reactive than secondary. Secondary is more reactive than primary. So that's why option A is the right answer here. So next question is, chlorobenzene on heating with NaOH at 300 degrees centigrade and high pressure gives. So chlorobenzene has formula this. So when this reacts with aqueous NaOH at 300 degrees centigrade and 673 Kelvin of temperature, I told you already in the synopsis itself, haloarenes are less reactive towards nucleophilic substitution reaction. However, to increase its reactivity, we have to maintain high temperature and pressure. Under this high temperature and pressure, so here high pressure. So here Cl will be replaced by OH. So it become phenol. It become phenol. Hence the correct option here is A, phenol. So next question is, phosgene. Phosgene is a common name for. So I told you, using chloroform you can prepare phosgene, you can prepare DDT, you can prepare chloritone, war gas or tear gas. So like that, so many important properties are there in case of chloroform. I told you so many times in the classes itself, and already we written one test on this haloalkanes and haloarenes in the I think in previous 10 days back. So in that I explained so many properties in the of the chloroform itself. So poison can be obtained by oxidation of chloroform. So when chloroform CHCl3 upon oxidation, so in presence of sunlight, so it removes it helps to remove the HCl here, and one oxygen is added here, it becomes COCl2. This is what poison gas. The common name of this poison gas is carbonyl chloride. Hence option D is the right answer. So next question is, chloroform on reduction with zinc and HCl gives reduction, that means addition of hydrogen. So chloroform having formula CHCl3. So when this reacts with zinc in HCl, so zinc can be obtained converted into zinc chloride by taking two chlorine atoms. Among them one chlorine is here and one chlorine is eliminated from here. This hydrogen is added to here. It becomes CH2Cl2. So this is what methylene dichloride, geminol dihalide, methylene dichloride. So hence option D is the right answer. So thank you students. So still if you go through with the various reference textbooks, you may get plenty of questions. Solve all the questions, and if you have any doubts, kindly ask me. So thank you. I will meet you in the next chapter.